Okay, here's a classic Calc 3 problem. It's a double integral. It's the volume of a solid, and you have a surface on top, and there's a region underneath, so you got to figure out what the region is, and you integrate twice, and you figure out what that volume is. So, the first step here is to figure out what that region is, and artwork is your friend here. So here's your xy axes. Here's y equals x, that first curve. And here's y equals x cubed. So you can see how these two curves naturally bound that little region there. And that's very interesting, right? It's interesting that those curves intersect in 3 places and that you actually have 2 different little regions. And in fact, I'm going to tell you that because we're in this weird situation where here the cubic is on top and here the line is on top, we actually need to split this into 2 integrals. So what I'm going to do now is figure out where these 2 curves intersect. I think you can see where they intersect, but I think it's helpful to see what the technique is in case the curves are harder. You set the 2 curves equal to each other. I have x cubed equal to x, and I'm going to solve for the x's. X cubed minus x is equal to 0. That's the best way of getting this done. You factor it out all the way, and now you can see that 0, 1, and -1 just pop right out. So there are my 3 points of intersection for those 2 curves. And like I said, this integral is going to have to be split into 2 because it changes from one curve being on top to the other curve being on top. In other words, here are my 2 regions. X varying from 0 to 1, and then for each little x, see how I drew a little stripe there? If you fix an x between 0 and 1, y will range from x cubed up to x. And that will be, like, imagine a whole bunch of little vertical stripes all along here. The second region on the left is where x can be anything from -1 to 0, and then y ranges from x up to x cubed. And so we have all these little stripes over here. And here is that double integral brought to life as a pair of iterated integrals. And so I have the 2 integral symbols. This is the left-hand region here. I have x varying from -1 to 0. Can you see how I have those limits on the outside to match the dx? And the y varies from x to x cubed. So this guy is set up just right. But I also need to add this volume over here, x ranging from 0 to 1 and y ranging from x cubed to x. Okay, now that I've got, to me, this has always been the hard part. So I've got these double integrals set up and I'm ready to rock this. I muck with the stuff in the green brackets first, ignoring the outside integral symbols and the dx's. And so I am going to take the antiderivative with respect to y, right? Can you see how the 3x plus 4 didn't change at all? You just slap parentheses around it and you throw a y on there. Reverse power rule. And you've got your evaluation bar over here with the x and the x cubed. And same over here. So it'd be the same antiderivative, different evaluation limits. So here's what you get when you plug in those evaluation limits and you get an x cubed minus x in parentheses here and an x minus x cubed over here. And what I'm going to do to make this a little easier on myself is actually distribute both of these polynomials. Because as everybody knows, reverse power rule is the best. So from here on out, these integrals are a joke. You just got to mind your fractions. So you get, like 3x to the 5th over 5, and then you get x to the 4th minus, I'll spare you the details. You know how to do this. At the end of the day, this volume is equal to 3/5, and this volume is equal to 7/5, and of course that adds up to 2. And so here's where I give you a little warning. You see how these volumes are different? You might be tempted to think that because this region here is so symmetric that maybe you can cheat a little. Maybe you could take this integral and double it or something. But that's not true. If you were to grab Wolfram Alpha or something and plot z equals 3x plus 4, if you were to plot that surface, it would be equal to a slanted plane. And so as we move in the direction of positive x, that plane is getting higher and higher. So this guy is going to have a way higher volume than this guy. So that's why these volumes are different, and you actually do have to do the two integrals separately.